Me, as always. I'm going to continue to build the poker tool today. I'll have to organize my thoughts because there's a lot that I thought about yesterday. I'm gonna put some music and I think I'm gonna stay 1.5 hours and then I'll see if I'll take a break or stop streaming. Let me put some music. So yesterday it didn't work, the script that I was doing, because of the memory. I think, I'm not 100% sure if I did everything correctly. I think I did, based on, like, I read the code and I tried to think about what could be wrong, but I thought I did everything right, but the problem was just the memory. But there is a chance that there was a loop there in the recursion, and then that I didn't realize for whatever reason based on the base case. So yeah, what I did was something different. I did manually. I think I created another script, and I think it was on this file that was already created, but I kept modifying and trying to understand how it works so I can understand the connection between the different ranges. And I think I understand it now, and now I'm trying to think about better ways to do it, because it might be the case that I'm not going to be able to build the tree from here, and maybe it's because I'm using Python and then it takes more memory. I'm not really sure, because obviously I can build it with Pio directly, so yeah. But what I'm thinking about doing now, I think I have to remember everything that I did, but I think what I'm gonna try to do is create the tree structure now. And I think I'm gonna try to remove some information from this, because the two essential pieces of information I think that I need is the node ID and the decisions of each hand. So each node has a strategy, which is the actions, which I realized that I needed as well. This node ID here, because I do need this thing here, and then also the children. So each node has to have all the actions that it has, and then the action has to be the dictionary of hands and their frequencies. And those hands and their frequencies are going to be percentages of the overall frequency of the range. And that's how it works, and I learned that by doing the simulations, by playing around with the simulations. So the way that it works is that you have, for each node you're gonna have a bunch of different actions, and then the sum of the actions should be 1, which is 100%. So, and that 100% is gonna be from the range of the current node. So let's say you have a hand that it plays, it gets to the node and it plays, the frequency is 70%. So that 70% is going to be split between the actions, but the value of the actions are not going to be the value of the split itself, is going to be the value of the percentage. So for example, one action is going to have 50%, the other 50%, and the other one 0. So what that would mean is that on the child node for those actions, you're going to multiply the 50% by 70%, which is the value of the hand on the current range. And the value of the hand of the child node range is going to be 70% times 50%, which is going to be 35. So that's how it works. And then I'll spend a bunch of time thinking about like how to make sense of this with the data. And then I think that the way is probably to use this total frequency here, that it starts with this method, and then I had to copy this method to this class as well. So I'm not really sure if I'm going to leave on the other class or not, but for now I think I'm going to leave it like this. So this creates a dictionary with all the possible combinations of cards, initialized to 0, each one. And that's the total frequency. And then what I do is every time I add a child, and this is another thing that I'm not 100% sure yet, but because I'm trying to think if it makes sense to combine the add actions with add child. I made another function called add actions that would only add the actions, and then this function would only add the child. But then I thought more about this, and I think that they have to be connected because each child is dependent on the actions. So you can't have an action and not have the children that is correspondent to that. So every time you add an action, you need to add a child as well. And every time you add a child, you need to add an action because they're the same thing, the way that it works in Pio. So if you check here, for example, then the node ID is going to be this, and then these are going to be the childs of this node here. So that means, and this, like if you put on the show range, I think, or show strategy for this node here, is going to show the ranges for each one of these actions here, the frequencies. And then the show range for this node is going to be the total value of all of this. So these are going to be in percentages like it is here. And then the percentages are going to add to 1 for each combo of hands. And then the value of the range itself, of the card itself, is going to be of the next iteration. So let's say, for example, it bets here and then it calls. The value of this, another, don't remember. I think yeah, is in position. So the value of this range here is equivalent to the percentage of this range here. So it's equivalent to this range, because obviously that's the only range that continues from this point on. It doesn't, the whole range doesn't continue. So you multiply the percentage of this with the value of the overall range, the frequency of the overall range here, and then you get the frequency of this, the overall range of this node here. And then again, the actions are split between the percentages of the overall range. And this is why it's very confusing and was kind of hard to figure out, because the way that the nodes are set up and the way that it shows is kind of confusing when I'm using when I was using the Pio solver connection to figure out. But I think that I'm pretty confident that this is the way that it works. But now I have to think about like how to traverse the tree, or how to add actions, because there's two different things. One is the thing about memory. This is I think the biggest concern, because it might be the case that I'm not gonna have enough memory. And there's also a lot of other stuff that I thought about, the combinations. I'm thinking about making another class that contains all the combinations and then updating cards based on the combinations instead of the actual combo, because that would allow me to get the data for all the flops instead of just the data for one flop. So like the correlation should be with the amount of data you have. The less data you have, the more like broader you need to be, because then it allows you to optimize the amount of data you have. So if you don't have a lot of data, it's better to classify hands based on groups. So for example, top pair or flush draw or things like that. And then based on those frequencies, then you node lock instead of node locking with the combo itself. But then obviously it becomes a lot more complicated. But what this allows you to do is to, instead of only getting one flop, you get the data for all the possible flops. And then you just, it's like making an approximation. And because the way that I think now is I'm probably not going to have data in the beginning to be able to only study one flop and all the actions of the flop. Like even if I have the actions for the flop, it's not going to be, even if I have the actions for all of the hands in the flop, it's not going to be enough to make conclusions. Like, and I think that you need like a lot of hands to be able to do that. So it's probably better to approximate and and also think about frequencies instead of thinking about the specific combo, which is not ideal, because then obviously it doesn't allow you to get very specific in the way that you're gonna node lock. But if you think about the combos or the frequencies, then it allows you to have an idea. But then you have to put more assumptions into the simulations. But yeah, so every time that I find a hand in the data, so first I think I'm gonna filter by position. I create the filter at the beginning of the script to only include one position versus another position to look at the data, and then get the ranges from those data. Not sure if the ranges are, I think I'm gonna create the simulations first. First I'm gonna do it with this simulation, I think, here. The one that I have here. And then I also have to think about the approximation of the bats. So I'm gonna have to create an algorithm for that as well. But I think I'm gonna do it for this specific spot here. But I'm not gonna do it with the board, I think, only with the actions. But this is the problem, is because they're interconnected. Like the reason why it's challenging is because the cards on the flop are gonna change the frequency, they're gonna change the range, the dictionary of ranges. But maybe it doesn't matter because I can leave all of them, regardless of what cards exist there. But I'm not 100% sure. I think that would work with Pile. You just translate. But let me think. So I think I'm gonna try to get the positions for this one. Did I? Sorry, yeah. So at this one I don't remember as well if I put the standard bats for. Maybe I should create one with the standard bats I have, a simulation. Because that's another thing. Then if to create the simulation I'm gonna have to figure out the algorithm to add lines. Since I think I'm not gonna be able to do it with the creating the tree because it's gonna take too much memory, but then I'm not really sure. Okay, the way that I'm thinking about updating now is just updating one path at a time, let's say. And then like that way, or a certain amount of paths at a time, and that way I don't need to reconstruct the whole tree. I can just update certain paths based on the data. And then I can put some amount of times that's, or put some limit on the amount of times that I'm changing the frequency here. And then once the limit is reached, then I call Pile Solver and update the strategy. And to set the strategy, you just put it is in the same order of show children. So show children shows the most aggressive action first, and then the least aggressive action last. And is a list of Pile Solver ranges, which are the sequences of floats. So the strategy here is going to be the same thing. So you need to get all the children, all the possible actions from the current node, and then set all the possible actions for the current node. But that's another thing that it gets a little bit complicated, because if I only want to update one action, then it gets really tricky, because you have to think about how to get, because I'm going to have to get the strategy first for the node with some of these methods here, probably show children. I'm going to have to get the show children, then, or maybe I just get the strategy for the node. Yeah, I get the strategy for the node. Because there's, I think I erased the other command, but there's a command that allows you to get the strategies. And then once I get the strategies, then I have to see, like based on the order of the index, which one is the one that I'm trying to change, and what other ones I'm going to leave the same. And then I just replace the one that I'm trying to change with the other ones, and then I put I create that and put that on the set strategy. And then you have to lock the node so that when you run the simulation again, it doesn't change the strategy that you just changed again. And then after that you run again. I think I haven't tested this one out because I need to have the strategy here. And then I was thinking about if I could use something like made up to put here, but I think that I can do that, but I think it's better to try to figure out how to use the data, update with the data. Then after you save, after you run, it's gonna solve again with this node locked, which means it's the strategy that you're placing there, and then it's gonna find the Nash equilibrium against the strategy that you just locked, and then you save the simulation again. And then I'm saving with a different name so that I know. Like, I'm gonna do it at first with one simple. I think it's just focus on one simulation first. So probably I'm gonna have to. I'm gonna need to have the simulation here. Maybe I'll do it manually. I think. Yeah, I think that's what I'm gonna do. I'm gonna run this thing and then I'm gonna build the simulation manually. And then I save. I try to automate the process for one, and then I save, and then I compare the solutions to see if it worked or not. That's probably better. And then once I have that, then I can think about the the general cases. Yeah, but I think I'm gonna do it manually because otherwise I'm gonna have to figure out how to do the add lines algorithm, and I don't want to do that before solving the tree because there's two different ways. One way is just to manipulating the strings for the add line based on the paths, so converting the data structure into sequences of lines based on the paths of the path. And the other way is to create the tree, and then the add lines path are gonna be the traversal of the tree. So depending on whether or not I can create the tree, then it changes which one I think I should do, I think. But this one I'm not really certain as well, this add child method here. So the way that I'm making is based on the action and the range. So if I want to add an action for a node, which I'm going to do from this data probably. Yeah, that's what makes sense, because this data I'm getting from the bats, I'm getting from the data. So these are the bats that are used most often based on the data. So then I get these bats, and then from these bats I add the childs here. So I create the root node, which is going to be the flop with the positions of the player, which is what happens on this class here. And I just have to think about like the most amount of things that I can remove, because I want to make as simple as possible. So I don't have to put information that I don't need here. And that's the reason why I removed starting pot from the poker node as well. Because I think the node itself doesn't need to know the size of the pot. I can do this logic here on this class. And I need this logic because I need to translate the bat sizes into the correct thing here, because the node is weird, the calculation. It's cumulative bats based on the amount of player which each player invested. So, and also you need to increase the size of the pot and know the fact abstraction of the size of the depth of the tree, I think. So let me think. Yeah, so I create the roots with the roots has these parameters first, then sets the both players as in position, out of position, get the ranges, effective stack, and all of that stuff, and then I create a function that adds the childs, and the function then is going to be based on the actions. That's the thing. So the standard bats is this thing that I got from this one, I think. Let me run this. Okay, yeah. So I'm printing twice here. Okay, I think I printed twice just to see if the donk was removed. Yeah, because you need to remove the donks for the player that is in position. So I got this structure of bats here, and then I create a function that receives this as an argument, or gets from the class itself, and then adds the actions here on this class based on the actions here. And the tricky thing is the sequence of and this is the part that I'm not sure, because I'm not sure if I'm gonna have enough memory, because for each it gets really big really fast, because you have 49 turns, which is 52 cards minus 3 from the flop, 49, and then we have 48 rivers. So all possible actions are 48 times 49, which I think is around 2400. And then based on those, you have to multiply by the bets you have on the flop. I think because each line for each turn and which river is going to be different, so we have to multiply all the actions based on, I don't know how many actions, but so 49 times 48 plus times a bunch of different possible actions you can have from the flop to the river, and it gets really massive. And I knew that from the beginning, because I know that it takes a lot of memory to build the trees, but like I thought if I was able to do it from the solver, I would probably be able to do it from here as well, but maybe that's not the case because they're using a different programming language and the code is more optimized for memory or something like that, or it can be another possible reason. And I'm not really sure if this is the best way also, like maybe there's a better way, because I thought about the tree because it makes sense, but it might be better to just use another data structure or update in a different way that doesn't require, because I don't need to build the whole tree to update. It would be better to be able to build the whole tree, because then I can build the tree from scratch. I don't need to save the simulations, to cache the simulations, or to use the simulations that I have saved to node lock. So it would be better if I could build it as well, but it's a lot faster, I think, if you just update if instead of concerning with the whole thing, with the whole simulation, I can just think about one path at a time and then I update the paths. But one path at a time seems inefficient, that's the thing. So, but if I want to update all the paths, then I think it becomes too memory expensive as well. So that's why I was thinking about the limits, where like when I'm going through the data is like is going through the paths of the simulation each time. So for each hand there is a path, and then based on the path that you follow through the hand, you increase the frequencies of that specific hand. And the way you do that, and the reason why it's kind of confusing is because I need to put this total frequency here, because the actual value of the frequency of the range is going to be the action times 100 divided by the total frequency. So, and this is kind of hard to understand. So let's say you have, for this particular node here, let's say it's this node of the tree. So you're going to have bat 120 and bats 100, no, bat 40, I think. 48. And then you're going to have check. So let's see, you have the hands like ace of spades, ace of clubs. So each time, let's say I'm analyzing a hand and I'm going through the hand of the data, and then the person has this hand. This is another complexity that I have to deal with, which is to know like what is the player. And I think I'm gonna do this based on in position and out of position. So check first to see if the node is in position or out of position, and then update accordingly. But this is something that is confusing. I have to think more about that. But let me explain this first, and then I'll think about that. So let's say that the player bats 120. So let's say initially everything is 0 because there's no hands. But that's confusing as well, because in Pio solver is not going to be 0. It's going to be a value here of these frequencies. But the reason why is this value is because the solver solved everything, obviously. So I think it initializes everything as 3333, the Pio. And then as it plays with itself, it changes these frequencies here based on the overall range. But let's say I start with 0, 0, 0, because it's just easier. I'm not going to be doing percentages, that's the thing. It's going to be like the only way to find the percentages is based on the frequency of the data. That's the problem. So that's the reason why I can't initialize to 33%, because there's no way for me to know like what is the proportion. I guess I can initialize to 33%, but then it becomes a more difficult calculation. Because each time that this hand is played, it's not like you're increasing 1% for the hand. You're increasing like 1 times 100 divided by the overall frequency, which is the total amount of actions. So not only I have to add this, I have to add something else that tells me how many times this path was played, because that's the only way that I'm gonna know what is the correct distribution of each action for the total amount. And that's the thing that was kind of difficult to think about. Because with Pio directly you don't have this, you have the percentages already. But if I don't have the total amount of times from the data, how I'm gonna know like every time I play a hand, or a hand is played on the data, how I'm gonna know what is the correct proportion to increase the percentage of one action and decrease the percentages of the other actions. That was like really confusing to me, but I think that's how you do it. You just keep track of all the times that the hand was played, but I'm not really sure if that's the efficient way as well, because then it goes back to the whole problem of the amount of data. Because in this example, then if there's only one hand, for example, then, but I think it is accurate, because it's a representation of the way that people are playing based on the data. So every time someone plays this hand, betting 120, you increase the frequency here by 1, and then you increase the total amount by 1. And because the other ones are 0, then this is going to be 100%, which is going to be 1. Maybe it's not, it's not actually times 100, because you already get the value in Pio. But if you want, because this is going to be 0.7, for example, let's say, in the percentages in Pio. So I don't need to multiply by 100, because it's the actual value. But yeah, So this would be 1, and this would signify 1%. But then let's say someone plays again, then increases this one, and this becomes true. Now it changes because this is going to be 1 divided by 2, which is going to be 0.5, so it's 50%. And this is 1 divided by 2, and is 50% again. So even though it increased by 1 here, it becomes 50% for each one, because now is the percentage of the overall total of times that the hand was played in the data. But then the problem with this is that is the other hands, I think. That's the issue. Because let's say I only have data for this hand here. There's more times that this hand was played in the data than there was that this other hand here was played. Then now it becomes an issue because this is going to be 0 for each one, but it's not an accurate representation. So that's the whole thing, tricky thing about the optimization of this. Because I think in order to be able to make it really good, I have to combine both the pile thing and my thing. So like this has to be equivalent to the percentages in pile, but then only switch on when I have the data. So I think what I can do is create a function outside, because the whole problem and why it's difficult is that I not only have to think about all of this stuff, I have to think about the overall context of everything else. So like it's creating the tree and then navigating the tree to populate these nodes and then retrieving these nodes and using these nodes into the pile simulation. That's what makes it really hard, I think. So, but I think that this way is probably gonna work, where I initialize everything to 0, all the actions to 0, and then I start updating, and then based on the amount of the total here, I can do based on the value of the total. Then I know based on the value of the total how relevant the data is gonna be for each hand. So if I have one total that is 20,000 and the other one that is 5, then obviously the 20,000 is more reliable than 5. So I can create a limit outside that determines that for a threshold of hands, you update the values based on here. And I'm just thinking about that now, and I didn't think about this before. So the best way is probably going to be a combination of two. So I need to have something here that gets the strategy first, and then create an algorithm that compares, or that based on this threshold updates only the values on the main strategy, based on the ones that are more relevant in the data. And that's going to be really challenging, I think. So I'm trying to figure out what stuff should I do first, because there's so many things. And also wrote down a bunch of things here to help me remember all of this stuff. Or maybe I should have showed this one instead of doing the other. I just remembered this now that I had wrote down everything to understand. But then the problem with this, let me talk about this thing here. So the way that I'm updating the child is I get the action, and this is, I think, how I'm going to populate the nodes based on the data. So for each node, I'm going to get the actions based on this bats here, and then I pass the action, I pass the range. If there is no range, if I don't have the range based on the data, and this I think is good, because let's say I want to build some range outside, let's say, just build one specific range for one node, and then because I might want to create a range without necessarily using the data, just create an arbitrary range just to automate the process of node locking. So let's say, for example, with combos, I can create ranges that determine that every time there is a bat of this size, for example, then I'm going to shift the distribution to have more top pair, let's say. So I can design a range like that, and then I can automate all the process, because I pass the range here to node lock all the nodes that are possible based on the bat size. So there's like an infinite amount of things you can do. But then if there isn't this action range, then I just create the range from zeros, and then I can create a new node here. Before there was it was passing the node and then adding the node, but now I'm creating the node on this function based on the action. So, and I haven't tested this, so it might be wrong, so have to see. And I'm not really sure, again, like I said, about the design decision of mixing together the process of adding the children and adding the actions, but I think that this is how it should be done because they are the same thing on the Pio simulation, so I think that's the best way probably. But then here I'm getting the... I'm looping over this dictionary that I just created of hands and frequencies for the action, which is going to be, the key is going to be the action, and the value is going to be the dictionary of hands and their frequencies. So let's say here's bat 120, then here's going to be the dictionary of hands, of ace, king, ace of clubs, king of spades, let's say, with the value of the frequency initialized to 0 in the beginning. So I'm looping over the hands, which are the hand here, and the frequency for this dictionary here. So the action is the value here. And then based on that, I'm creating the value of the new node, the range of the new node based on the equation that I just talked about, which is going to be the value of this thing here times the value of the frequency of the range of the current node. So initially everything is going to be 0 if there is no range, because it's just like multiplying. It's as if you're saying that the specific hand is never going to be on the child node. So because the frequency of the hand is 0. So when you multiply 0 by the current frequency, you get 0. So the next child node is not going to have the hand. But if the frequency is different, let's say 50%, then you're just multiplying that 50% times the frequency, the 50% of the current node times the frequency of the new range, and then you get how often that hand will show up on the child node. So that's why I'm doing this thing here. And this creates the dictionary with all the frequencies of the range for the new node, and then I get the action based on, I got the ID, just putting the action here at the end. Then I check to see if it's in position or out of position, then create the new node with the parent itself, because the parent is going to be the current node, and then I append it to the children. I think maybe I should create a soft flop here. I'm gonna use it on the other methods, but so let me. I think I'm gonna run this, and then I'm just manually gonna create, and then as I talk about the other stuff, I wait for this to be solved. The problem is I need the ranges as well. And because I'm gonna update based on the ranges from the data. So let me look here. I'm just gonna manually go through the ranges. There isn't a lot of data, so it's probably not gonna be correct. But I think I'm not even gonna show once I already have more data, but I don't wanna put here because I don't wanna show. I'm not really sure. Maybe I'll show in the future, but for now I think I'm not gonna show it. So it's VLAN. Oh, I have to go here, I think. Navigate through here. So VLAN is big blinds. No. Yeah, maybe I should create from the scratch. How they clean this and clear all. And then I'm gonna pick an arbitrary board, I think, just to do the simulation. But then, yeah, with the data I'm gonna have to figure out, I think, because I'm not gonna have data for one specific board. So I'm gonna have to think about how to generalize show all possible boards, and then just I think I'm gonna count. I'm gonna have to do the grouping thing, I think, or maybe just count the frequencies of the hand and their actions, and then like disconsider the board. And then I just use the preflop range as the starting range. The issue with that is that obviously I'm misrepresenting, because like let's say the person raises with 7-6 suited. It's a very different thing to raise with 7-6 suited if the board is 5-4 true, than if it is ace king true. So, and if I count based on just the action in the hand, then I'm not taking that into consideration. So the conclusions are going to be incorrect, but I think in the beginning I can do that, because the whole point is just to see if I'm going to be able to automate the process of node locking. And then once I do that, then I can think about creating the other class and just abstracting things to be by hand strength instead of doing the whole thing. But so maybe I should pass through this thing here, because I can just I can't open the range from there, so I'm gonna create another folder here. I think I'm gonna delete this one, because I was just using to reverse there the thing. And then I'm gonna copy from here to villain position is big blind versus button. Obviously not enough data, but I'm gonna leave it like this. And then hero, single spot, then button versus big blind. I'm just gonna manually create this stuff. Very interesting. But here, that's the thing that I was talking about. Like, obviously I don't play like this, but the issue is that just the frequency of the hands, like the more data you get, then the higher accuracy, the better the representation. And that's why I think that the best combination is probably choose like the default values, because here would be a different story if I just like had my standard range and then I was updating the range based on the data that I get. So increasing and decreasing the frequencies based on the data, because then it's just like it's like increasing the resolution in the picture. It's actually very similar to convolution, I think. These kinds of things, because everything is related. It's just the matrices and pixels. But yeah, that's I think a good way to think about it. So the more data you have, the better representation of the picture you can get. But it's better if you start with the pictures and then you train the model that way, and then you use the variations of the pictures, and then you get better results than if you just try to train it from scratch. So yeah, unless you have significant amount of data. So I think it's exactly the same thing as convolution. Not exactly the same, but extremely similar, I think. Yeah, now let me think about... I think I have from here the parameters. Oh, this is weird because... Oh no, this is true bet, yeah. as it is 160. And then effective stack. So here I don't have the boards for the data. Maybe I can get from the board frequencies that I did here. This one is the one that shows more often. I think I need to put a space. Let's see if it works. Yeah. So now put the bats there. So I'm in position, so I'm not gonna put the flop bats. Maybe I just put true. This is the thing, maybe I should decrease or increase based on whatever one is in position or out of position. So maybe I should do this call after I do all of this, and then I put the values, the limits for the bats based on whoever is in position or out of position. So I can limit the flop bats for the player that is out of position, because that makes the size of the tree smaller. But I think I'll worry about all this stuff after I build the simulation, so that's... I'm gonna put 29 here. And then raises, so that the tree is smaller. So that this runs while I do the other stuff. Because I'm gonna have to wait for it to finish anyway. And maybe I should update one side first, and then I'll worry about the other one. 16, 36. And this I'm not 100% sure as well. Because I can think about times where I used 16%, so it's kind of weird that it is there. Maybe I made a mistake on the calculations, but I think I reviewed a bunch of times and I couldn't find an error, so I think I'll only be able to know that once I have all the data, like more data. 36, 57. And also the river is also weird. So like maybe there is a mistake with the adding the pots. I guess I'm gonna be able to see as well from the actual value of the bat. I'm gonna be able to remember in game if the value is the same or similar. So here, instead of using, I can just use the donks instead of using the bats. So I don't need to filter again. I can just put the donks there. I do some logic that gets the donks when it is the flop for the player that is out of position. This works as well. Yeah, so I think this is it. Now let me save this. Yeah, this is correct. Yeah, now let's see if there's enough memory. I have, I think, 64 RAM, but usually there's only 40 available, I think. No, I think I have 48, not 64. Yeah, I have 48, and then usually there's only 40 available, or something like that. It's already a lot. And the biggest problem is that it takes a lot of time, but I think it's not that big of a deal, because I think the biggest issue is if I can't build the simulations from using Python, like programmatically, because then I have to save the simulations first. But I think that it doesn't matter that much, because as long as you have, yeah, it requires a lot, so that's the problem. It's enough memory. Yeah, maybe I should search for how to, like, I wonder how they do these estimates. Maybe they have something. Because I need to do that as well. I think there's a command there to know the size. So maybe I should I should check this command first and then do some algorithm that removes the batch sizes based on the... But the biggest challenge is that stuff should decide which ones to remove. But I was gonna say that I don't think it's a big deal that it takes a long time to run the simulations, because realistically you probably only need like 5 or 7 simulations at a time, because, or maybe, yeah, if they are solved from the flop, because then you can just train one spot at a time, and then you don't need like to hold a bunch. And then all you do is just delete the ones you have from time to time and add new ones once you feel like you train the specific spot enough. So I think I can do removing the flop bats first, or raises. This is probably not going to be enough. So I think removing the smaller bats first is probably better, because they take more space. Because the smaller the bat, then the more raises you have. But I think just removing that one is not going to be enough, so I'm going to have to think about which ones to remove now. Probably the ones in the river, 17, and from both players. It feels wrong to me. Oh, this one actually decreased the size a lot. Yeah, so flop obviously decreases the size more, because then it compounds the effect throughout everything. It feels weird to me, because I know, like, I use more sizes on the river and bigger sizes as well. But maybe it's one of those things where I'm just because there are this other sizes in the data. So maybe those are the ones that I use the most frequently, but then I don't realize. Could be one of those things. I think I'm gonna remove this 16 here from the turn. But that's the challenge, because this process of removal depends a lot on the bias. Like, it's hard to create an algorithm, because it's more of a subjective thing. So how, like, because I think now that I can find something here that determines the size of the tree. So I could call that method first, and then from that method try to build the simulation first with these parameters, and then from the but then I would have yeah, this is another process. I shouldn't think about that now. I think about that later. If I can node lock, then I'll go back and think about the process of building the simulation. But what I could do is just build, then check to see if there's enough memory, and if there isn't, then I create an algorithm that reduces the batch sizes based on some sort of heuristic, but then it's hard to decide which heuristic to use to remove the batch sizes. So I think I'm gonna remove the 17. Maybe it's better to remove my sizes first, because obviously I can control my sizes, but I can't control their sizes. So I think that's one of the heuristics I can use. So it's obviously always better to decrease your sizes first and then their sizes, because then you have a more accurate representation of how they play, and then you can control how you play. Okay, so it builds, so I'm gonna run. But now, I think. Oh, let's see. Let me see if I can get the lines from here. I think I can't unless I go over the add lines thing. So maybe I have to figure out the algorithm for the add lines first before I think about the tree. Because what I'm thinking about now is I don't need to know all the bats, I just need to know the bats for the current simulation to update them, because then I can create an algorithm that gets the one that is closest based on the data. So let's say someone bats like 35% of the flop here instead of 29, then I would just round to 29. But if there was a 37 here, then I round to 37, so whatever one is closest. But I do need to know which bats are here though, because I'm gonna be able to only gonna be able to no lock based on them. But I guess it does matter, because I have to create the actions based on the amount of actions that are there. So I have to create this dictionary of action ranges based on the actions that exist on this simulation, because I'm going to use that to set the strategy later. And the question is, how do I get the... Because the one that it has to be the same one that I'm using here. I think I'll do manually now, and then I'll think about this later. Either I have to... Yeah, because either I'm gonna have to build the simulations programmatically from there, from this data, which is the easier thing, I think. I just have to figure out the add lines algorithm. But then I'm not sure if I should try to figure out the add lines algorithm now, because then there's the whole thing about the tree. I maybe should figure out the add lines thing now. I think it's just gonna be a cumulative bat. Let me open the file there that I just saved. Just see. I think it's just gonna be the bats, like, but the thing. The question would be, how do I traverse the paths without... I think I could create heuristics for when the lines are finished. So one is when they fold, the other one is when it reaches the stack depth, and the other one is when it reaches the river and there are no more actions. So when it reaches the river and is either a call or a check or a fold. I think those are the heuristics, and then from that point you just alternate between the possible bets and raises for each player. Yeah, but then you need to create a tree structure, I think. That's how... Or maybe there's another way, if you just make a if statement or something like that, control flow. So that you alternate between auto position and in position, and then you check. So the relationship that I need to figure out is how to determine the change of actions, like because I'm thinking about navigating the possible actions. So from here there's gonna be flop, the bats at the beginning. So bats for the player that are in position in the beginning are all the actions which are gonna be bats or checks. And then from that you have the potential actions of the next level of the iteration. So if they bet, it's going to be a raise or a call, but if they check, it's going to be a bet. or a check. And this is a tree structure, so it's hard to think about how to create an algorithm that is not going to create a tree. But maybe I can create the tree, but the concern that I have is just the memory thing. But I think for just creating the tree, maybe it takes less memory than to do what I was trying to do before, because I was trying to save everything on a dictionary for each time, and also navigate the whole thing, like the whole object from Pio, I think. So if I just create the tree based on the bats, like create an algorithm that creates the tree based on the bats, and then the lines are going to be the sequence of events there, and then for each path so I think the better way would be to get all possible paths and then navigate through them and add the lines while navigating. So create depth first search, for example, and each iteration of the depth first search is going to be a line. So when it reaches the base case, it adds the line to a string, and then after it adds all the lines, then you put that on a file or you use on the simulation. And it should populate the tree. But then that's the thing, because maybe you don't need to create the nodes to populate the tree. It's just the tricky part is just figuring out how to create the heuristics to add the sequence of actions, because it's kind of confusing. Because all the actions are dependent on the previous action. So to find the general thing that works for creating the actions based on all the possible situations is hard. I'm not really sure if I should do that now or not. The thing is the bat size is here, so let me think. One thing that I can do now is just do manually here and mimic whatever I put here. So I test based on this data structure, so pass hard code the data structure and pass that to this class here, instead of the one that I get from the data. And then once I figure that out, then I'll do the rest. I think this might be the better approach, I think. Because I'm more curious to see how the node locking is gonna work. And then I'll worry about creating the simulations later. But if I can't create the simulations, then that's the question. How would I do this process that I'm thinking about now? Yeah, I would have to create an algorithm that gets the bats from here, and then... But this would involve the add lines, I think. So this is what I was trying to think. If there's a way to get the possible bats from the pile. Like get this structure here from these commands. But I think the only way is going to involve the add line thing. Or the process that I was trying to build of the show children, trying to navigate through the show children to get each action. And then I'm not going to have enough memory, I think. That's the problem. Yeah, so I think the better way is just to create based on the data that I have, because that way all the simulations are going to have the bat sizes that I have here based on the data. I think that's the best way. So I need to create something that's maybe let me see here if there's a way to calculate the size of the tree. I think it's probably down there on the build tree thing. And so this is the hard part, is it is cumulative. The sides are cumulative. That's why it's confusing as fuck. It's that, and not only that, and the whole thing about figuring out all the possible, like how to determine the heuristic for changing the player, the possible actions for each player, based on the line that was taken so far. I guess you need to determine based on the nodes probably. So if it's a bat, then you have the different responses. So you look into the raises, the calls, and the folds. Which folds are only going to be one, call one only going to be one, and then check. So if it's a bat, you have these possible options. If it's a check, then then depends on if it's in position or out of position. And I think the add line doesn't take into consideration the cards, so it becomes easier, I think, because you can skip the turn. You just would go to the next street, let's say, but then you can make, like, if the in position player checks, then you have all possible bats from the. It's actually not that difficult, I think, now that I think about it. Just determine what possible actions you have for each kind of action. There is a consequence, and then based on that, you check the data structure you have for depending on those conditions, then you get those possible actions, and then from those actions. But the question is, yeah, like how to determine which one to take each time. That gets harder, I think, because you need to add all possible ones. So maybe do some multiplication, but multiplication doesn't work because you have to add the bats and it's cumulative. So you need to keep track of the sum of the values that we're taking so far. But I think whenever there is more money invested, if it's a bet or a raise, then you increase the size. Otherwise, you just put the same value. I think like it's gonna be difficult, but I can see a way to figure it out, I think. Can I add line? Yeah, but this doesn't have. Maybe I should manually create a big tree that I don't have enough memory, and then I test the build tree here. Just see what's gonna happen there. Either way, I'm gonna have to figure out the add line thing. But the thing that is confusing, or not confusing, that I don't know, I'm not really sure, is I was able to create the tree, and then I'm loading that tree, and then it runs out of memory because of the algorithm that I made there to explore. So this is the thing that it doesn't make sense to me. Like maybe I made a mistake on the algorithm. Like that's very possible as well. Because if I have enough memory to build the tree and to load the tree, then I should have enough memory to navigate through all the nodes based on the show children thing. And this is the stuff that, like, maybe I should try to create a simple version of that. Because I'm concerned that I might have made a mistake on the base case. Because there I'm returning children, but it might be, I'm returning when there's no more children. But it might be the case that somehow it gets me into an infinite loop. And that's why it ran out of memory. Because it's always going back to the same spots. And then the reason why it's hard to know is because it depends on, like, it can go to several different spots before it gets to the one that completes the cycle. That's the problem. So one thing that I'm thinking about doing is creating the algorithm again and then creating a cache to put the visited nodes, and then if, but I'm not really sure if that would be good as well, because maybe for exploring recursively you need to go back to ones, to nodes that you have visited before. That's the thing, not really sure. There's so many different things to think about. Yeah, I think it's not, there isn't a method that I can. You should be estimate tree size here somewhere. Maybe I missed it. Maybe I missed. Oh, estimate tree. So this is the method. But you need to build. But yeah, so this is a good thing because then I can build the. I can do an algorithm that removes the bat sizes. I think the heuristics I can use is one. First, always remove from myself the bat. But then, like the issue is because then, let's say for example that I remove 2 of my bat sizes, then it might be better to remove 1 of their bat size because you don't want to oversimplify as well on one side and leave the other very complex. And I think that's good. But I think one of heuristic is always remove my bat sizes first, then remove the smallest bat size on the flop first. If it's lower than 33% or 30%, something like that. Because I think 30% is reasonable, so. But if it's like 5%, then it might be an error or whatever. But this is the thing, because if there is this bat sizes, then it might be a problem before as well on the calculation of the thing. Yeah, but as far as I could check, and I checked multiple times, I don't see how the calculation would be wrong. Because I'm increasing the size of the pot each time, and I'm getting the percentages based on the actual data. Like the amount of the bat size. So like it should be the correct percentage based on the flop, based on the pot or the bat. And as far as I remember, when I was checking with Pio, it is the percentage here as well. Like the value there is going to be the percentage here. Maybe it's the whole cumulative thing, but I don't think so. Because from the actual data, the only thing that changes is the flop, is the pot, not the bats. The way that I'm getting the data. So if there's a bat of $1, for example, like it wouldn't be more than $1 the correct way to get the percentage, I think. Like increasing whatever was the highest bet in the flop, and then increasing 1, and then getting the percentage of the flop based on that bet. I don't think that makes sense. I think that's just a Pio thing, but I could be wrong, obviously. So it's kind of bothering me that. Yeah, but I'll figure this out later. But I'm not really sure if I'm gonna show it on stream or not. Maybe I'll talk about it, but I'm not gonna show it once I think what I can do is just change the data off stream and then check with my own data. But I only want to do that once I have everything set up, so that I don't because once I do that and I have the actual data for the ranges, and I guess I can run again as well and just rewrite everything, so it wouldn't be a problem. So maybe I'll do that. Like, run with more data upstream and then check to see if the bets are more likely to be correct or incorrect based on the data, and then go back. But it does feel very weird to me, these sizes here. And especially the smaller ones, for both the turn, the river. Yeah. So, what I was thinking before. So now what should I do? I think I'm going to hard code the bets that I have there. And I'm gonna change here, and then I'm going to pass those ones to this range 3 here. Then later on, once I figure the no locking part, then I think about the algorithm to reduce the bet sizes based on the... Yeah, but that's the thing, because... Yeah, this part would come only after I have everything set up to build the tree. Because, and it's not even what I'm trying to do now. I'm just trying to analyze the data. But yeah, because I would have to call the methods for estimating the tree, so I would have to have everything set up, and I would need the algorithm for adding the lines. And so I should probably hard code everything here instead of doing like that, because... Oh, the other thing that I realized is just I can use the standard bets here. Instead of passing or creating these values of the starting pots. But maybe, yeah, I'm not sure which one is better. Yeah, I think I did this way because I would use after. I thought I might use after the sizes. Starting point and effective stack, but maybe I won't. And so I'm just gonna hard code everything on this one, and then I'm gonna use the hard coded values to try to figure out the no locking thing. And then I'll think about the other stuff later. I guess I'll just copy this thing here. Put the actual values. I'm gonna comment everything out and then put the actual values here. So I can pass the stuff. And so what I'm trying to do is to build this simulation here. I choose these values to build the tree and to see. I want to update one of the nodes with the strategy based on the data. And once I do that, then I can get the strategy from that node, convert the ranges into pile format, and then crawl this script here and pass that, which I'm putting here as an argument, and node lock the simulation and save the simulation. So that's the thing that I'm trying to achieve now, I think. So first I'll do that, then I'll worry about everything else. Yeah, so I'll get the node ID from the tree here, from the poker node, and then from this node I'll get the strategy, which is the action ranges here, and I will have to create an algorithm outside of this, I think, to delete the total frequency, and to sort the actions based on the one that is the most aggressive first, and then the other ones, and then convert those from ranges into pile format. Then once I have that, then I pass through this, which is going to be the list of those things, and then I test to see if it works. The thing is, I'm not really sure if this should be passed as a list or not, because it doesn't say here. I think it should just pass as a string instead of a list. It probably makes more sense. But I'll have to see. I think I'll worry about this once I have everything set up. Where is the information? Let's see. I think I closed the tab. Yeah, here. It just says that you should pass node ID and then n times the floats. So maybe I should pass just one big string instead of passing the list. But that should be easy to do, obviously. Or I can pass the list and then convert inside of the function itself. You just loop over the list and then add to another string the values. It shouldn't be hard. The other thing that I was thinking about is if I should, but then it's gonna be too much work, but convert everything to NumPy. Because I was watching some videos, I don't remember from who, but that said that if, and it makes a lot of sense, and I also agree with that the more things you do using NumPy and Pandas or different libraries like that in Python, the faster it's gonna be, because then you're just using, because those libraries use CPython, I think, which is pretty much more closer to C than to Python, so it makes everything faster, and it vectorizes everything, I think. So I was thinking about whether it's worth it or not to try to convert everything to NumPy, to use NumPy, because I'm using a lot of loops here and a lot of stuff, and it makes everything slower. So the other thing that I was thinking is whether or not I should convert this to Rust, but then the problem is that I think it's just like I think it's not worth the time invested. That's the thing, because I'm not that invested into poker. I'm just doing this to I'm more doing this to train software engineering skills than to improve at poker. I think it's going to be helpful, very helpful to win at poker as well, but then like this is a question of whether or not the time invested is worth it to translate everything. But maybe I'll do that eventually. But the reason why I was thinking about this also is because of the memory thing that happened yesterday. So maybe if I try to optimize everything, then it becomes, not only will be a lot faster, but then it might allow me to do more stuff than if I am just using Python. I think I can remove this show children as well, just here, and this as well. I think I left it there because I was thinking about looping through the children. Maybe I'll do that as well, because that's another thing that I have to figure out. But first I'm gonna try to just pass the strategy. Then I'll figure out an algorithm to determine the relevance of the data, and then just put the additional information that is more relevant and leave the rest as the standard solution. So load the strategy from the solution first, then loop over that, then based on whether which position that I want. I think it shouldn't be that hard because I can sort first, and then I'm gonna know based on the index which place to swap the information. It shouldn't be that hard, I think. So let me think. Yeah, let me go back to the other stuff. So here, let me copy this. Maybe I should put with spaces here as well. Oh, actually, maybe it does matter. It's probably better with spaces because then I can use split. And then it's gonna be easier to calculate the turn later, I think. The reason why I put together is probably because of... Oh, maybe, yeah, the data is together, so I have to put together. I think that's... makes sense. Let me see again here. Yeah, the data is together, so it's better to make it together. So here, I should probably put the names as well, so it's easier to know which arguments it is. And then here, I'll put hero, I think. Yeah, hero. Oh, it's the other one. And the other one, I think, is villain. Yeah, I'm gonna have to leave those ones here. I think I'll be right back. Back. So hero range. Now let's see. Yeah, now I don't understand why. Oh, positional key arguments, that's why. Hmm. Is this missing the thing here? Oh, here. Yeah, so now what I was gonna do. Yeah, now I'm gonna manually remove there, I think. The ones that I remove. And the bats I'm gonna leave because it doesn't matter. I'm gonna use the donks for the villain. That was just the 16. Not sure if the order matters as well, but I think it doesn't. Yeah, so these ones I'm gonna leave it like this. I'm just gonna remove the rays. And those are here. Oh no, those are here as well. Yes, I think that's it. $29, $48. Oh, there's also this all-in threshold as well. It's kind of annoying. So now let me think about it. Single raise, single raise. So I need to go from this data structure to adding all the nodes. Maybe it's helpful if I put them side by side. And this is the part that is difficult. I'm gonna think about the... I think the search is different than creating the thing first. And that's the question. Do I want to create first or do I want to search first? Or just search like... Yeah, because I don't want to create the whole thing, that's the thing. But if I'm using the data, I have to create the whole thing, I think. That's the question, like the process of searching the node, is it gonna be... It has to start at the root and then go. But like maybe I can, because I can create one function to add just one particular path at each time, and then another function that creates all the paths based on the standard paths. And the whole thing is the memory thing. I think that's maybe creating the one path first. Which is gonna be, I'm gonna receive the node ID from the hand, I think. But I need to create all the ranges so I can update them, I think. Yeah, so I need to create all the node first. Maybe it should be another name. Create sim or something like that. So I think I need to call the add child. Oh, what? I don't need to pass the standard bats because I have the standard bats there. So I need to think about how I'm going to translate this into the process of adding the nodes. And it's very similar to the thing about adding the lines, I think. So maybe I should write down the heuristics here. I have to think if I'm gonna pass anything as an argument or not. I think not, because I have everything on the class already, I think. Yeah, I have the starting point, have this effective stack. The thing that changes as well is the value of the bat, because it is cumulative on the solution. So instead of, because here is going to show one value, but then here is going to be the cumulative bat, and that's the one I'm going to put. So if there was a bat of 100 on the flop and another one of 100 on the turn, then here would show B, the E, and 200. So it's the cumulative value. So, and that's the action that I'm going to add on the node. So I should add that action instead of adding the 100, add B 200. So I have to convert here on this function as well, I think. Yeah, but I think I'm not going to receive anything, so I'm going to create this. And here I'm going to put the heuristics, so... The other question is whether I use like breadth first search or depth first search or something else, because of the recursion. But I think that... And maybe the thing about the recursion is that you can hit the stack depth or the stack limit because of the recursion, so I'm not really sure. But I think that trying to do recursion first is better. Then I think about the base cases first. And folds. Folds. Effective stack. Oh, calculation. Effective stack has been reached for a bat. If so, the other one is the river, I think. Let's see if I missed any. Check or call on the river. Check, call, or fold. Yeah, but fold is already there, so I don't think I need the. I don't need to put the fold on the river because it's already the first base case. Yeah, so I think those three are the base cases. So the question is, how do I know where is the current value? Do I know this on the nodes? Maybe I should put... I think I had that before and then I removed. Oh, but I can know based on the node ID. That's how I know. So I do the calculation here. Calculate cumulative bats and translate to string mode or notation. Right. So before I'll translate, I need to calculate the Aulin thing. Yeah, I think the way that I think I can see the path now to do it. It shouldn't be that hard, I think. The hardest part is thinking about the information that I have to pass each time to each node. But the way that you do is you start with the root node, and then based on the potential actions there on the self.standard bats. Yeah, but the tricky thing is how you're gonna do the recursion to navigate between them. But I think you do that based on the heuristics, which are the stuff that I was talking about before, where depending on what action it is, you have the other potential actions. And this is the stuff that I have to think about. Like how to determine the data structure, what are the potential pools. You create a structure of if-else statements, like control flow, based on the type of the action. So the type of the action is going to be the if-else statements. So when it's going recursively, it checks to see what kind of action it is. And then the base cases are the point where it reaches the end, which in case you just return the node ID. But then how do you return and then you add the node, I think. Yep, no, but you would have to add the nodes recursively, I think. That's the thing. At each point you add the nodes, a different node with the current ID, and then you change the node ID based on the actions that are happening. With the translating, so you do the translating first, which is this part here. First calculate if the bats is 60%. First I need to know what kind of action it is. So the way that I'm thinking about doing this is I'm gonna have another function here inside it, and then I'm gonna pass through this function, I think. Maybe I can just call the self create tree as well, but then I would need to require that, I think. Yeah, that doesn't work because I need to pass through this function the action as a parameter, and this one I don't want to pass the action because I'm gonna get the actions from the sender. So I don't want this one to have any arguments, I think. So it's like I handle the situation here first, and then I pass the actions here, and then here I do the recursion based on the actions. I'm trying to think if that makes sense or not. I think it doesn't make sense to put a parameter here, because then it would be like separating the standard bats from this tree. So if I pass an argument here, then it would be like a different design decision to do the calculation here first on this script and then pass the action as an argument. But that's not what I want to think. I need to use the standard bats that I have from the class, and then with that I pass the action. But the question is, do I need to pass? I think I do need to pass an action, because that's the only way that I'm going to be able to update the node ID each time. That's the thing. But then I need to decide, like, I'll probably put a condition to see which player is in position or out of position. But then that's the thing, because I have to start. So I need starting possible actions to start the recursion. And then from those options, I do the recursion. So maybe put the DFS on a loop, and then create a structure with all possible first actions, which is going to depend on the position. But shouldn't that be included in the recursion? That's the thing. Or I can just do none in the beginning. Like a default parameter equal to none in the beginning. And then I pass. Actually, let me think. Yeah, now I'm not really sure. There's one way to put action here, and then I make it equal to none, and I just call this function recursively, or I create this one and pass. Because the tricky thing is, I think it's better if I figure out how to do the recursion for all of the bats, for all of the decisions, regardless of the first action. But then I'm not really sure if that's if I can put that on the. I think it doesn't make a lot of sense to put inside of the recursive function though. That's the problem. Because then it would do the calculation all the time, for every step of the traversal, and I don't want to do that. But the logic is pretty much the same, I think, or very similar. But based on the type of action that it receives, is gonna do some things. So at each point, I think I need to have all the information that is necessary to create the node. So I create the node in the beginning. Yeah, that's the problem. What's the current range? I think I just create the empty range at first for each one. That's where it gets tricky, because then it depends on the context outside of this, of how it's gonna work. Actually, I do. The first one is gonna be the preflop range. So that's the one that initializes everything. So maybe it should be outside the beginning. Yeah, this is fucking hard. Okay. I think I should create the first one outside with the ranges for the in position and out of position player. First nodes. The thing is that the in position is always going to be the children of the out of position, so I need to create the first out of position node first. And then based on that, on all possible actions of the out of position player, then I create the first node for the in position player, which is gonna have the same range for all of the nodes because it's the same range. And then based on that, once it gets to that point, then I start doing the recursion, but that's a tricky thing to figure out. Like, the problem is the limit there. I'm not sure if it's better to try to do it inside of the recursion. Try to think about to do inside of the recursion, even the first step. And how I'm gonna get the current range, that's the thing. Because it's the whole thing that is based on this strategy here. So I'm actually adding childs based on the action. So I need the action for each one. Yeah, so in the first one I'm gonna pass the preflop, but on the other ones I initialize everything to 0, I think. But then the issue... but I think it doesn't matter if the frequencies are 0. Yeah, because the frequencies will be 0 in the first. Because there are no actions in the data. But this is gonna change if I have the... but actually it doesn't change, it doesn't matter, because I'm not gonna use that to build the simulations. The only thing that I'm gonna use to build the simulations is the node ID and the actions, but I'm not gonna use the ranges. That's the thing. So I can create the structure of add lines without having the ranges, even if all the ranges are 0 in the beginning. The only thing that matters is that the only thing that matters for updating is, like, then I can figure out how to get the parts that are relevant. So it doesn't matter that all the ranges are going to be initialized to 0 in the beginning. And I think that this is something that I have to do either way. Like, I can't just not initialize this. That's my concern here because of the memory. Because I'm creating a lot of empty ranges, so it's kind of like a waste if you're not going to use it. That's the problem that I had before. So now I'm trying to think if there's a better way to, like, save space here and not initialize the range, like just leave it without the range, and then just create the range once you have the data. But then the problem with that is because how I'm gonna update the frequency. I think the updating the frequency, I'm not gonna add the child, obviously. I'm just gonna traverse based on the children of each node. So it's a different thing. But maybe when I'm traversing through each children, I could check to see if the... But then the problem is that it changes the whole design if I think like that. That's the difficult thing to think about. Like, I'm thinking about now where I don't create the actions in the beginning to optimize, and then I only create actions. I only create the ranges once I have the actions from the data, or once I have the actions from the traversal. But then yeah, the ranges specifically, like I would have the actions, but I wouldn't have the ranges. So the actions, let's say, instead of being like this, it would be initialized to 0 here. So if there's a check, for example, then instead of being the range, it would be just 0. Maybe I can do it like that. And the reason why I'm thinking about this is because of the add child here, because I'm gonna have to change that child. And then I'm thinking about when I traverse here, let's say I put all the children, I create the tree based on the actions, and then I initialize everything to 0 first. But then I get the data, and I get a hand from the data, and I wanna update the range from that path, from the node ID. How would I do that? So I go through each node, and then I check to see if the action is 0 or not. If it is 0, then I create the range. Yeah, maybe that's a better idea. It gets more complicated, but I think it's better. And then here, instead of doing this, I just put... but then I can't do this thing here. That's the problem. Yeah, because it's confusing, because then all of the ranges are interconnected based on the frequency. That's the problem. Because once you change the data for one range at the top of the tree, it like navigates through the bottom. It's kind of like a ripple effect. Because then it changes the frequencies through all of them. Yeah, but then that's the thing. Like, I think I need to just do this separately here. Probably. Because this, it can't be on the adding. That's the thing that I was talking in the beginning, that I wasn't uncertain about. Whether or not to mix the add child and add the action. Because exactly of this problem here, I think. But I think I do need to separate them now, thinking about it. Because it just makes a lot more sense if I initialize everything to 0, it's a lot faster. And then once I have the action, once I have the hand, then I initialize the range with the data from the hand. So I set that a specific hand to 1 and all the other ones to 0 and the total to 1. And then I run this algorithm here where I update the other ranges, and the thing is I would have to traverse everything from the point that I update one range. It has to update all of the other ones. So I create another algorithm that traverses the children, goes over the children, and then updates them. And then the children would have to update. But then how the... I think it only updates one level, because then the other ones are dependent on the action that exists on that child. So if there are no actions on that child, then it doesn't need to update the other ranges on the node, because it's like the nodes that don't exist yet. And I don't need to explore the whole tree, because all that matters to me is at one particular level, the strategies of that node. If there are actions there, because that's gonna be what I'm gonna use to node lock. So from my point of view, it doesn't matter if there isn't the whole tree here. Let's say it stops here, because all that matters is that I have the frequencies of these actions at this point for this range. And this would be the current range of the node, so I think it's much more efficient if I do it that way, I think. So I'm gonna do it like that. But the issue is that I'm gonna have to write a bunch of comments here to remember this stuff, because it's quite confusing. Especially this calculation here. So this would be 0 here. And now I create another algorithm that checks to see if the value exists. Let's think. And that's gonna change the other one as well, the other class. Yeah, so the way that I'm thinking about it in the beginning is just to adding the actions. I still create the node, but then I just... And the thing is, what is going to be the current range of the other node? It's going to be 0, I think. Everything's 0. Yeah, because that way you separate the process of creating the nodes. I still have to create the actions here, but then I separate the process of creating the nodes and creating the ranges for the nodes. So at the beginning, initialize everything, but I think it's still better to create the ranges for each node. Yeah, I have to pass the range anyway. So I'm gonna have to create at least one range for each one, but then it's more optimized because I don't create the actions until it is necessary. And then the ranges are just gonna be initialized to 0 for each new node that I use the addChild method. Yeah, because this is going to be a consequence of the actions of the parent. So to update the ranges, I have to go from the parents to the other ones. And I need to create a method that traverses the tree every time I update an action. Yeah, and that's the process of navigating through the node ID. Because that's what you're doing. So when you navigate, so the function is going to receive the node ID and it's just going to navigate through the children based on the node IDs. And then at each action, it initializes the range if it doesn't exist, and initializes the value of the hand to 1. And if the range does exist, then it just changes the value. So I put an if else statement there. Yeah, that's a lot better, I think. Oh, it's gonna be the name of this function. I think I'm gonna put here. I think just add actions or update actions. And then I'm gonna put the stuff that I have here. I think this one continues here. I think it's just this thing here that I have to pass there. And now let me think about it again. It's kind of confusing. So this one I do it like this, and then it's gonna only initialize the range for the node, and it's gonna be 0 everything. And the ranges for the action I just... So I think that's a much better way, actually. That way I'm still making the child dependent on the action, but I'm initializing everything to 0. Unless I'm passing the range already. But if I'm passing the range, then I should do the calculation, I think. To update. I guess I can call the function. Update actions. But then I have to think about what the arguments, or if it would be better to separate. Yeah, because I think if I add the range to this level, then I would need to update all the other ones. So maybe it's better to separate, because then I need to get the total frequency, and I need to update the total frequency as well. Let me think. Because this is already a child, so... Yeah, but the range of the child depends on the parent. So what I need to do is update the parent, not the child. I need to update these nodes based on the range that is added here as an action. So I think... the current range of these nodes on the new action range added. Yeah, so here I'm probably gonna do is just get the values, check to see if the values exist. If they don't, then initialize the total frequency, which is gonna be equal to the frequency of this. And then I change the value of the current range to be the calculation there. But actually, it wouldn't change anything, now that I think about it. Because it only matters, the calculation only matters for child nodes. But it's very confusing. Because the child node also has its own range. So I would have to update the range of the child nodes. And that's the thing. Yeah, so this range here has to go here. And then I do the calculation based on the way that I did before. So let me think. And this will be the action range. And what would be the child range would be the action range times the current range. It would be this, I think. Which would be this new... I think here it makes more sense to put child range. So here I have to loop, I think. Do the same thing that I did here. Yeah, that's the thing. I think I merged the two because I was trying to avoid doing that. The same thing twice. But I think I can't really... Like, this way is much better, I think, because then the whole memory thing, it becomes more efficient, I think. Because here I'll do the method again, where, because that's the only way to update the frequency, I have to update the values and other ranges, because they're objects. So... And the value of the current range of the other one is gonna be the action range times this. So I think it's gonna be like this, and I'm just gonna have to do this twice here. And this would be the action range. No. Yeah, this would be the child range. Yeah, so I'm looping over the range, and if it's not on childs, let me do this. Self the current range times the frequency, which is this one. Yeah, I think that now it's correct. Now let me think about this. That's super confusing. I think the only thing that changed here was instead of creating the initializing the range, but doesn't matter that much. Because I still have to initialize the ranges. That's the problem. So maybe the other way makes sense, more sense. The issue is that they're interconnected, so I think the other way makes sense. Like there's no way to optimize so that I don't create the actions, because the range of the node, the child itself, is going to depend on the range of the action, and I need to initialize. So maybe the other way makes sense, more sense, I think. The way that I was doing before. But then the concern that I have is that I'm not going to have enough memory to add everything. Let me go back to the way that it was before. I think it was like this. No, but it's not coming back, so I'm gonna have to remember what I did here. Instead of this was just the method there. Create current range. Oh, that's the only thing that I changed, I think. Just instead of initializing, I was creating the empty range. But I think that the thing is I can't get away from doing this because I'm gonna need this to do the thing anyway. To update the values of the child node. So I think that it has to be like this. Yeah, but I think from the other class it doesn't change much. It's just an optimization thing. So what I have to do is for each action there on the parent class, the poker tree, I don't pass the range in the beginning. So it's just going to be initialized to 0. And then I create another function to update. And here I also changed. It would be... It's just complaining because it's not using the self. So now I have to think about how I'm going to determine the boundaries. Because I have to initialize the first ones with the ranges that I have from this class. These 2 ranges here. And then I need to call the add child on the root and then pass the action. So this is, I think I'm gonna write down there the stuff that I need to add each node to create each node. The other thing I'm not really sure if it's a need is street. That's the other stuff, is how I'm gonna determine the turn and the river. I think it's better instead of street putting turn and river. and then making a condition that checks. Or maybe I do a different type of node as well. I'm not really sure what to do. But yeah, I'm not 100% sure if it matters or not, because I'm obviously updating the ranges, but yeah, maybe it does matter because of the cards. Because I'm not really sure the way that I'm gonna do outside of this with the data. So if I do a more generalized way, then let's say I have like ace of spades and 3 of diamonds. But then for the current boards, the turn is gonna be ace of spades at one point. So if the hand on the data is ace of spades and 3 of diamonds, then obviously that wouldn't work. It would be updating the wrong thing. So I have to check first if the turn for the nodes, or for the node ID is if the current hand contains the. But I think that's a simple check. You just check to see if the string is split. Yeah, I'm not really sure because of the way that I'm getting the hands, the data. But I can create something that just checks to see if each combo is in the node ID. And if it is in, then I skip the hand. But that also depends on the way that I'm gonna do based on the data there outside. So maybe I'll remove the street for now. It's not really necessary. Oh, the street is useful because of the river. But I think I can do the logic on this class here. Yeah, maybe I should create the logic here to determine which street it is on the recursive call here, based on the actions. But then how do I determine the amounts? Yeah, because that's the thing. On the standard bets here, I don't have the turn and the river. No, obviously, but I have to create all of them, obviously. So I need to create a function here. So I can create a function to get all the possible turns and all the possible rivers. So I'm gonna need that anyway to do the calls here to create the whole tree. Yeah, so probably what I should do is create this function here, and then I should remove this from this class, I think. I'm gonna remove it for now, then if I need later, then I'll put it again. I just want to have as little, I think, is the way to say it, little information as possible on this node, so it's less complicated to add and to traverse. It's already complicated enough with the actions there. So here I would make gets. Maybe I should separate, or I should get all the combinations, I think. And this should accept the... it shouldn't accept because I have the board already, the flop. So just from the flop I created all possible combinations. So now I think also I should do this part outside here. I should do this when initializing maybe this class. I'm not really sure if I'm gonna use this method here on this class as well. Because the ranges are gonna be created here. If I don't pass, it's already gonna create. Unless I wanna create the range here for whatever reason, to maybe for the data to pass the range. I'm just thinking now as well about the, again, this is the thing about design, where like I'm making this class should be dependent on a flop, but it might be better later on to generalize the class and then just make methods inside of the class instead to create the flops. That might be better. Because that way this class can work as like a search thing, where it only creates one path at a time and then updates that path on the nodes, the data for the path. And then as the data goes, it creates more and more. Maybe that's better. So I make the class based on the position instead of the flops. Because if I'm going to generalize later as well, it might be better to do it like that. But then it this is the issue, is because it changes everything if depending on the way that I'm gonna do. And it depends on the data. This is one of the problems I have, is because like I start thinking about all these possible variables and like all this complexity. Like my mind goes faster than what I can do, I think. Then I end up getting stuck, I think. And this is something that I have to be careful with, but it's still like a paradoxical thing, because then it obviously depends. But what I'm thinking about now is like it's gonna depend on the gradient. So the gradient of data should determine the accuracy of the software. So the more data, the more accurate it becomes, and the less data, the less accuracy. But then the gradient of the data is going to change the structure of the classes because it's interconnected. And that changes the design. So it makes it harder to think about which way to build things. Obviously I can build the two different parts, but then which one, maybe there's a middle way to do it. So I think the fundamental thing that is going to change here is this thing about the flop here. If I have less data, then it might be better to just make it based on the position. And the type, it doesn't matter because I have the starting pot and fact of stack. But if I can make based on the position, and then from the class, instead of yeah, but then it would change the poker node as well, because then I would have to update the hand classes instead of updating the hand ranges for each thing. And obviously I could create different modes as well for both types. Maybe it's better separating into two different classes, and then from these two different classes I create a mode outside, and then depending on which one I use, I update it accordingly. But I think that might be the better way. So I should create another class, I think, that uses the poker node as well. And then that class instead, or maybe a variation of poker node, I just create another file. It might be better to separate, but it might be better to do that one first, because it would be better for less data. But then instead of having the ranges, I would have the ranges for each action. I would have the hand strength for each action. Yeah, but then it wouldn't be dependent on the flop. It would have to be a general thing about like just populating the hand strengths based on the frequency of actions, and then creating the template of no locking, and then using that template to no lock to create a script outside that runs through the flops and no locks them, or through trees, different trees from the flop, and no locks them. But I think, yeah, that's the thing. I think I can't do a flow between the two. That's the thing. So this one is more specific, but then I use the template to populate this one. Yeah, but I think I'm over complicating stuff. I'm gonna focus on this one first, and then I'll think about everything else. Yeah, so I think I'm gonna think about this off stream. The thing that I'm stuck now is determining whether at what point to start the recursion. That's the challenge here. If I should start outside here and then do recursive on this function. Because the starting point is gonna be, I have the ranges on the starting points, which are the preflop ranges. And then based on the actions, the first actions, those are gonna be the ranges. So starts off with the auto position player. Then based on the actions that the auto position player can take, the in position player is gonna have the same range against all those actions. Oh, fuck, I just realized that actually I'm doing things wrong. Because the problem is I have to skip one level. It's actually a lot harder, I think. Because here I'm updating, unless I do separate nodes for in position and auto position. That might be the way. As I just realized this now. Because they alternate, so the child range is not gonna be... This whole calculation I was talking about is just for the same player, so that's the problem, is that like if I bet here and then it calls, then this range is gonna be the one that is changed based on this action here. But it skips one level, which is the other player. And the way that I'm doing now, I'm updating this range based on the calculation of this true. That's an issue, but I think I can create two different trees, one for in position and one for out of position. Because it's gonna be a problem here if I'm gonna have to put the logic to see if it is in position or out of position, the node. Or just skip one. It gets really complicated, I think, to do all these updates. I think I'll have to do for each player. And I think it makes more sense to do for each player. So maybe instead of poker tree, I call player tree. Because I only want to node lock. Maybe I'll want to node lock both players at specific instances, but I think it makes more sense to separate them. And it's better that way. So in that case, I will remove here the in position or out position. And then I create the trees for each one separately. And then when is the other player to act, I just change the node ID. So that information is still gonna be in here, because it's gonna be part of the node ID. But then I'm not gonna, and that's even better if you think about it, because then I use less memory to create the tree. So for node locking, this is fine, but then for building the tree is not. So I'm gonna have to separate the add lines thing. I'm gonna have to create a different algorithm that doesn't traverse the tree to create all possible lines, because then on this one I'm gonna leave the other player decisions without, unless but then I would make that outside if I do the two different players, if I want to node lock both of them. I think that's better to do this way, because then I don't have to change everything here or think about how to alternate the frequencies to change the range. It gets too complicated, I think. And the only thing that changes from the other player perspective is the amount of options that you have there. But the layer doesn't change, I think. It changes on the path of the tree, because if it's, let's say you have a bet and then you have a raise. Yeah, but then that's the issue, because what would be the child there? So maybe it does matter. Maybe I have to figure out how to put them together. Because if I leave one player left, then how do I determine which are the childs of this one? I think in Pio the childs are the actions for each part. But that's why it's confusing, and it was confusing to figure out as well. It's because it alternates them. So I think the way that the Pio does it is with alternating them. But then how do I update the ranges? It's gonna be very complicated. Okay, I need to update them on an interval. But the problem is if I leave one player out, then it's an issue as well, because let's say I bat and then they bat. If I have the children as the ranges that would happen if they, because the way that I'm doing the calculations is I'm multiplying there based on the, so one of the childs would be they call, which would be the child for this action here, for the bat, because I'm multiplying that range based on the range of the bats, and then I'm getting this range here. But then another child would be, but then I wouldn't capture this child here, which is when they raise. Oh, but no, it's the same range, I think. Yeah, it's the same range. It just changes the decisions. Yeah, but you would change the childs of that child. That's the problem. Depending on the other player actions. And the question would be, how would I navigate the tree if I skip one step? I think I can think about a way to do it, but then you just split the node ID and remove actions based on whether they are odd or even to determine which one is in position or out of position action. And then the node ID would be just the actions of one player, but then it gets really complicated as well. Fuck, how do I do this? I think probably the best way to figure out how to do it with this class here. Adding the actions for both players, but then I'm gonna have to change this function here. Because the range is not gonna be for the childs. The whole issue is this thing here. Because if I could remove this and just put the node here, then obviously it's easier. So maybe I have to transfer all this logic into the other function, into the other class. I will still need to keep a way to calculate. Yeah, but I guess I can do that on the other class. And then here I just add the nodes as children. And then I check to see on the other class if they're in position or out of position. And then I update the ranges that way. So each node will still have the actions here and would be initialized like this. But then this whole process of changing the ranges for each node would happen on the other class. I think that's better. But I think I would still need to create the whole logic to determine which one, because I need a way to get the previous range. So I update the child range of the child, the grandchild range on the parent class. Yeah, but I'm gonna do that, I think. So I'm gonna copy this function on the other one, just so I don't have to do everything from scratch. But then I'm gonna leave in the way that it was before, where this is just gonna receive the node, and then it's gonna make the parent equal self, and then append the node there, and then I'll move this function to here, to this other class. But the thing is, because the only way to update is to know which one. I think let me think. Yeah, the ranges themselves have to be connected with the... But I think what I can do is just cache the last one. I cache the last one, that's what I do. For each player. So in this function here, I put the outside of this other function. I cache the last range of each player, and then I update the current range based on the last range through the calculation by calling this function. So it calls the action and then does the updating process. But then I pass the previous range here. So this would be previous range, I think. So this function, instead of doing all of this stuff, it would get one range and then the action. Yeah, but I think no, it would get two different ranges and then get the new one for the current node. Yeah, so I think I'll delete everything here. Obviously I'm gonna delete this because then I can see the information for the node from outside. Like I can get the remaining information. Yeah, I think that works. You just remove everything. So this receives the current range. But then how would I update the hands? That's the thing. I think I can create another function for that then. And this one is used in the beginning to create all the ranges with 0, initialize everything to 0. Or to whatever proportion it has there, based on the previous range. And then I create another function that gets the hands, specific hand, and then updates the ranges based on the hand with the node ID. So it gets the hand and node ID, which is the path that the hand took, and then traverses the tree based on that path with the hand and changes the values of the frequencies of each range. And then you would need to only change at the current level. I wouldn't need to change the... No, but... Yeah, let me think. I think I would need to change all the ranges, because there's... It's very confusing, but if I change the frequency here for this range, for example, for changing to bet more, for example, for one hand, then it would change all these ranges here, both the call and the raise there, the whole range here, because it's the multiplication. But if the path of the current hand is not gonna go through all the possible paths, it's only gonna go to the path that it happens. So let's say, for example, I update the 46 frequency here for the current hand, but I don't update the childs. Then what's gonna happen is, for whatever path was taken based on the node ID, I'm gonna update all the ranges correctly because I'm updating the frequency for each one as I go through the tree. But then for other parts of the tree, I would still have the old range because it didn't change the grandchilds. But I think that I can do a method for updating them outside of the... I think it's easier and better if I do it outside of the nodes themselves, the method. And then I just think about a way to get all possible... Because I can separate based on... I can just determine if it's the in position or out of position. So it's easier that way. So if it is out of position, I do the caching thing, where I store one, or I can do a queue or something like that, where I store one node, one range at a time, and while I traverse the tree, it looks like it. Okay. I think I'm gonna stop here and think about this off stream. I'm not really sure if I should clean this or not, because I might have to use it later, and I don't want to recreate. So this is going to be different. It's going to be current range. And now I think this shouldn't be none ever, I think, because it is always required to, because the current range depends on the previous range, I think. Yeah, I'm gonna stop here. I'll think about this off stream. Maybe I'll come back today. I don't know. Probably not. So if I don't, I think I'm gonna come back Friday. And now what I'm gonna do, what I'm gonna focus on is on clarifying this stuff. Yeah, trying to think about how to create this function here of the recursive thing, and the separation between these actions, how to update the actions and the ranges based on the data, the frequencies of the data, and how to create the whole tree as well in the beginning. Like, at what points should I start the recursion based on the preflop ranges that I have here, and this data structure of bets here. So how to use the data structure with the preflop ranges to create the whole tree by using the depth first search or a recursive function to navigate through everything, create everything, all the possible decisions and childs, and yeah. So maybe I'll come back tomorrow, today, but if not, then probably Friday.